So in this proof, I'm going to do some coordinate geometry proofs of polygons, so showing that like quadrilaterals are like different types of quadrilaterals. So first it's like proving that a quadrilateral is a parallelogram. So to review kind of the characteristics of parallelogram, fundamentally it's quadrilateral where the opposite sides are parallel. And so that implies that the opposite sides are congruent, that the opposite angles are congruent, that the consecutive angles are supplementary. So again, we have opposite sides parallel, and that implies that the opposite sides are congruent. The opposite angles are congruent. Consecutive angles are supplementary, which means that these two add to 180 degrees, these two add to 180 degrees, etc. And then that the diagonals bisect each other, which is something that you guys are going to be working on for the try at home question. So if you're able to show any of the following, like the little check mark with the yellow, then you know that the quadrilateral you're working with is a parallelogram. So the first one is just that both pairs of opposite sides are parallel. So that's just like the definition of parallelogram by definition. So the second one is that the both pairs of opposite sides are congruent. So I'm going to show like why that implies that both pairs of opposite sides are parallel. So first, like we have, by assumption, AB is congruent to CD and DA is congruent to BC. Then we know that triangle DAB is congruent to BCD, and that's by side, because we know that AB, again, congruent to CD, DA congruent to BC, and then obviously BD is the same as DB. From that congruency, we know that angle DAB is congruent to angle BCD. Furthermore, we also know that triangle CDA is congruent to ABC. That's again by side. So again, CD is congruent to AB, DA is congruent to BC, and then AC and CA are obviously the same. And from that, from 5, we know that angle CDA is congruent to ABC. So from 4 and 6, because the interior angles of a quadrilateral always have to add up to 360 degrees, and now I know that like there's two pairs of equal angles. I know that if I pick any two of these at like one angle from here and one angle from here, any of those combinations has to add up to 180 degrees. And that's because if you multiply that by 2, if you're doubling it, grabbing like 2 from here and 2 from here, you get 360. Again, the sum of the interior angles of quadrilateral. So that's just, so I chose angles DAB from here and angle ABC from here, and then the other pair. So those are supplementary. That's what it means. Then from this, I can conclude that BC is parallel to DA. So the way that I can do that is that I know that, so I have BC and I have DA, and they're cut by the transversal AB. So because angle DAB and angle ABC are supplementary, so they add up to 180 degrees, again from here, that means that side BC and AD are parallel. Similarly, I can conclude that AB is parallel to CD. In this case, we're working with the lines AB and CD and the transverse DA. And because angle CDA, if you recall, and BCD, CDA and DAB. CDA and DAB. Sorry, I should have grabbed the wrong one from here. Just apply DAB to both of those. CDA and DAB, because those are supplementary. Again, I conclude that AB and CD are parallel. And then I know that ABCD is indeed a parallelogram because I just showed that the pairs of opposite sides are parallel. So that's like the definition of a parallelogram. Another thing that's sufficient to show that a quadrilateral is a parallelogram is if both pairs of opposite angles are congruent. And so I actually already proved this in the previous proof. If we just start at number 4 and 6, like we have these assumptions, both pairs of opposite angles are congruent. That's what this assumption is. DAB is congruent to BCD, that opposite angle, and then ABC is congruent to ABC is congruent to CDA, that's that angle. Then working from that, again, I can just go down to 7 and then 8 and 9 and get that those are parallel, and then it's a parallelogram. Another condition that if you're working with quadrilateral is sufficient to show that's a parallelogram is that one pair of opposite sides are both parallel and congruent. So I have a little drawing here. So I have ABCD, and that's a quadrilateral. I kind of drew in the dashed lines to the sides just to help with visualization. And I know that one pair of opposite sides are both parallel and congruent. So I'm saying that AB and CD are both parallel and congruent. So then angle DAB and angle CDA are supplementary, and that's the same argument as before, working with the parallel line AB and CD and the transverse AD, then because then the supplementary angle must add up, the side angles next to each other must add up to 180. So it's just like this image. I have this angle is going to be the same as that, and this has to add up to 180 with this. So these two add to 180. That's what I'm saying. Angle DAB and angle CDA are supplementary. The same logic, just working with the transverse on this side, angle BCD and oh no, sorry, not the same logic. Angle BCD and CDA are supplementary because angle DAB and angle BCD are congruent. Oh no, I'm sorry. No, it is the same logic as before. It's just BC is now the transverse. No, BD is the transverse. Sorry, that's what makes sense now. So BD is now the transverse. So wait, that doesn't make sense. Sorry, just to restart this proof. So AB is congruent to CD is given, and AB is parallel to CD is given. So then we can get that angle BCA is congruent to angle DAC because we consider AC to be a transverse intersecting the parallel lines BC and BC and AD. Then we get that triangle BCA is congruent to triangle DAC by sine angle side. And from that, we get that side AB is congruent to CD. And furthermore, angle BAC is congruent to angle DCA. And then that we can conclude that the side AD is parallel to BC because the transverse since like BAC is congruent to DCA, the transverse AC intersecting the lines AB and CD makes them equal, so then those lines being intersected have to be parallel. So then it's a parallelogram by definition. Okay. So the other way that you can show a quadrilateral is a parallelogram is if the diagonals bisect each other. And so I'm going to let you guys try this proof at home. Just moving this up. So next is proving that a parallelogram, so now you know that you have a parallelogram, proving that it's a rectangle. And to remind us, a rectangle is just a parallelogram where all the angles at its vertices, so all the angles at the corners, are right angles, and the diagonals are congruent. So if you can show that any one of its angles is a right angle, then you know that all the angles are the right angles for the following reason. So we have a parallelogram, two pairs of parallel sides, and then we know that this angle is right. Well, because of like these being two parallel lines, we know that then this angle has to be right angle, this exterior angle, which makes this interior angle the right angle. Furthermore, parallelograms, the opposite angles are congruent, so then that makes the last two angles right angles. So then you have all the angles are right angles. If you can show that one pair of consecutive angles are congruent, then for the same reason, kind of, you can show that they're all right angles, because we know that congruent angles are supplementary in parallelograms. So then them being congruent means they're both right angles. And then from before, opposite angles are congruent, so you show that all of them are right angles. Now finally, if you can show that the diagonals are congruent, then we can show that all the angles are right angles. I didn't write a formal proof, but basically you have a parallelogram ABCD. And we know that ABC, triangle ABC, is congruent to triangle DCB by side angle side, because we were just told the diagonals are congruent, and we're just going with the opposite sides, which we know are congruent since it's a parallelogram. So opposite sides are congruent. Then angle ABC is congruent to angle DCB. And as the angles are supplementary, again, because they are neighboring angles, then they have to be right angles. And then all the interior angles are right angles. And just a note, we can also go from knowing that a parallelogram has all interior angles being right angles to knowing that the diagonals are equal by side angle side. So let's say we have a parallelogram, and we know that all the angles are right angles. Then we can see pretty easily that triangle ABC is congruent to triangle DCB by side angle side, because we know AB is congruent to DC. Angle ABC, because it's right angle, and angle DCB are right angles, are the same, and then BC is congruent to CB, obviously. So then side CA is congruent to side BD. I'm sorry, not side. The diagonals. Diagonal CA is congruent to diagonal BD, and we're done. So finally, it's proving that a parallelogram is a rhombus. Just a reminder, so a rhombus is a parallelogram where all the sides are congruent, the diagonals are perpendicular, the diagonals bisect opposite angles, the diagonals form four congruent right triangles, and the diagonals form two pairs of isosceles triangles. So if you can show that one pair of consecutive sides are congruent, then that shows that all sides are congruent, because again, with the parallelogram, we know that the opposite sides are congruent. But then if you're told that, this one is congruent to this one, then that means that they're all congruent. If you know that the diagonals are perpendicular, then you can show that a parallelogram is a rhombus. So we know that the diagonals are perpendicular. So because we have that the interior angle is like 90 degrees, and then we know that diagonals of a parallelogram bisect each other, we know that these two sides are equal. So then by side, this angle, this side, and then like this side, this angle, this side, we know that those two triangles are congruent. So then this side is congruent to that side. Also, knowing that either diagonal is an angle bisector will also show that, oh, and so, sorry, then we go to the first one. I just showed that one pair of consecutive sides are congruent means it's a parallelogram. So the proof that if a diagonal of parallelogram is an angle bisector, then the parallelogram is a rhombus. I'm giving you a proof here. So I just drew a little parallelogram and I'm saying that AC is an angle bisector, which of course means that angle BAD and angle DAC, those are 1/2 of angle BAD and the same on the other side. So by the hypothesis that AC is an angle bisector, angle BAC is congruent to angle CAD, and angle BCA is congruent to angle DCA. And just to be extra thorough, we know that angle DAB is congruent to angle BCD because ABCD is a parallelogram, so the opposite angles are congruent. And then finally, we can conclude that all of those angles, angle BAC, angle CAD, this one, angle BCA, this one, and angle DCA, all those angles are equal because so these two angles are 1/2 of the angle that's the same as these two angles combined, which are 1/2 of each. So all of them are the same. They have equal measurements. Then we know that triangle ABC is congruent to triangle ADC by angle side angle. So ABC, I know that this angle is congruent to this angle. And then I know that this, wait, sorry. Sorry, so the first angle we're working with we're for the angle side angle that they're congruent. So for the side, I'm using the shared diagonal, which is AC. Then the angles that are congruent for ABC, we know that this angle, in ABC angle side angle, that's the ABC triangle, and then the ADC triangle, it's angle side angle. So if you flip them over, they're the same. They're congruent. So by angle side angle, they're congruent. So then from that, we know that AB is congruent to AD. Again, if we flipped it over, we know that this side has to be the same as this side. And so then ABCD is a rhombus because the four sides are equal, because I know that one long side, not one long side, but I know that one pair of neighboring sides are equal and those have to be equal to their opposite sides, so then all the sides are equal. And of course, four sides of a parallelogram being equal means that all of the angles are right angles, because, and along with the angle bisector, because I know that this is equal to this, so not even the angle bisector, but if we're considering the diagonal, this angle must be equal to this angle because it's an isosceles triangle. And then the same here, those two angles are equal. And then it would be the same here, sorry, where those two angles are all the same. And of course, so all of those like half interior angles being equals mean if I labeled it x, AX must be 360 degrees, which is also 4 of 2x equals 360 degrees. So 2x, which is what I'm saying is this angle, is 90 degrees. And then all of the angles are right angles. And so that's the end of this video.